Welcome to online Precalculus. Today, we're going to cover section P6, Rational Expressions. So our objective for this section is to specify numbers that must be included from the domain of a rational expression. And then we're going to start to simplify rational expressions, then multiply, divide, add, and subtract, and then talk about complex rational expressions and how to simplify those. And finally, simplify rational expressions that occur in calculus, and also with that is to rationalize numerators. All right, so what is a rational expression? So a rational expression is the quotient of two polynomials. And you can see some examples, right? So the polynomial could be just a constant on the bottom. The constant could be on the top. We could have variables on the top and the bottom, or we can have a more complicated polynomial on the top and on the bottom that you could interact with. Now, the set of real numbers for which an algebraic expression is defined is called the domain. Because rational expressions have division, and division by zero is undefined, now this is very important here, that's why it's in bold, we must exclude numbers from a rational expression's domain that make the denominator equal to zero. Okay? So with these expressions up here that we'll look at in a second, if the denominator, anywhere the denominator is equal to zero, is not part of the domain of that rational expression. So let's look at a few of these and find all the numbers that must be excluded from the domain for each rational expression. So anything that makes the denominator equal to zero must be excluded. So I can just take the denominator and just set it equal to zero. Solving for x gives me 2, which means that for this rational expression for part A, x cannot be equal to 2. So if we were to write this, we would say, here's my expression, comma, x is not equal to 2. Let's look at part B. Okay, so for part B, we again set the denominator equal to 0. And then when we solve it now, add 1 to both sides, take the square root, and now we get 2 answers, plus or minus 1. So that means that my expression becomes x is not equal to positive or negative 1. And you could write plus 1 comma minus 1 either way. And then for part C, we just again set the denominator equal to 0, and now we have a quadratic trinomial. We are going to factor this. So it factors into x plus 6, x minus 3, which makes x equal to negative 6, and x on this one equal to 3 with the zero product property. Okay. So now, those are the two things that x is not equal to, negative 6 and positive 3. Okay. So let's try our checkpoint problems. The first one should be fairly obvious. X is not equal to negative 5, setting the denominator equal to 0. For part B, x is not equal to plus or minus 6, setting the denominator equal to 0. And then for part C, right, we should probably look at the factored form of this expression, because that'll be a little bit easier to help us decide where the denominator is going to be equal to 0. So I just want to rewrite this in its factored form to help me out. And I'm going to get x minus 7, x plus 2 in factored form, which means that x is not going to be equal to 7 or negative 2. Should have wrote it the other way, right? Smaller to bigger one, but whatever, it's fine. So when we go about simplifying a rational expression, it's simplified if its numerator and its denominator have no common factors other than 1, negative 1, And you can use the procedure in the yellow box there to simplify a rational expression. So first, we factor, and then divide both the numerator and the denominator by any common factors, right? So we just cancel them out. So we factor and then cancel out any common factors. So when I'm looking at this expression and I want to go about simplifying it, my first step is to factor it. So this can factor, I can factor out an x squared, a common factor. That leaves me x plus 1 over x plus 1. And then I can cancel these two out, and my answer is x squared. However, when just looking at the answer of x squared, that doesn't really tell the whole story of this rational expression. You should also tell the reader any excluded values. Okay? So we're going to say that this function is x squared, but x is not equal to -1. Let's see what that means in a later chapter. Okay? Part B, again, let's factor this expression first, the top and the bottom. So the numerator factors to x plus 5, x plus 1. The denominator is the difference of two perfect squares. So that factors into x plus 5, x minus 5. These two cancel. And so my simplified expression is x plus 1 over x minus 5, comma. Now, it's a good habit to just write everything that x is not allowed to be equal to. I can see still this left over, I still see it can be 5, but the -5 got canceled out, right? The x plus 5 factor got canceled out. So I'm still just going to put that x is not going to be equal to plus or minus 5. Let's try some of our checkpoints. Same general idea here. Factor first. We're left with x plus 3. Cancel. So my answer here is x squared, comma, x is not equal to -3. For part B, the numerator factors with the difference of two perfect squares, while the denominator factors to x plus 1 squared, right? It's a perfect square trinomial. One of these cancels with one of these, and so my answer becomes x minus 1 over x plus 1, comma, everything, the only thing that x is not allowed to be equal to is -1. And again, I see that with this denominator here, but again, it's a good habit to just list all of the exclusions on the variable. All right, so this gets us now into multiplication. So if you remember how fractions multiply, the product of two rational expressions is going to be similar to multiplying two fractions together. So it's the product of the numerators divided by the product of the denominators. Step-by-step procedure is factor everything, cancel everything, divide numerators and denominators by common factors, and then multiply. So before you get into a big multiplication problem where you are combining a lot of things and you have a lot of factors flying around, cancel out the ones that are common to the numerator and the denominator. Simplify first before multiplication. What do we mean by that? Let's check it out. So we're going to start this with the left side. Nothing can factor times factoring the right part of the expression gives me x plus 1 times x minus 1 over the 3 can factor out, and we're left with x minus 7. Look at that. We now have a common factor of x minus 7 and a common factor of x minus 1. Now, when I multiply these together, right, there's nothing left on the first part of the expression. It's just x plus 1 over 3, comma, x is not equal to anything that made the denominator equal to 0 anywhere in this entire problem. So that would be something there, a 1, and something there, a 7. right? The 3 is not a variable, so it can never actually make the denominator equal to 0. Only variables, and only factors that contain a variable. Let's try our checkpoint problem. Again, for the first part of this problem, nothing cancels, or sorry, the denominator can factor. So that's x plus 2, x minus 2, times, now the numerator can factor, so that gives me x minus 3, x plus 2, over, this looks like a perfect square trinomial, it would be x plus 3 squared. So now there's two x plus 3's. So one of them can cancel with this one, and the x plus 2 can cancel with this x plus 2. So what's left over is an x minus 3 on the top, and those two. So x minus 2 and only one x plus 3, comma, x is not equal to anything that was in the denominator to ever make this factor, ever make the denominator equal to 0. So we got plus or minus 2 and a negative 3. And better to write them all in numerical order, so negative 2, negative 3, negative 2, positive 2, but you get the idea. So division, dividing rational expressions. The quotient of two rational expressions, if you remember how fractions work, is the product of the first expression and the multiplicative inverse, or reciprocal, of the second expression. So back to when you learn how to divide fractions, right? You multiply by the reciprocal. And you interchange the numerator and the denominator, so we find the quotient of two rational expressions by inverting the divisor and multiplying by the reciprocal. Now, one thing to mention is that if you multiply by a reciprocal, you're moving the denominator to the numerator and a numerator back to the denominator. So there can be more restrictions on the variable. So what does that mean? So let's look at this problem right here. So we're going to factor the top here. So that's x minus 4, x plus 2, over difference of two perfect squares, x plus 3, x minus 3. Now, I'm going to switch this to multiplication, and my fraction is just going to flip over. So x plus 3 over x minus 4. Okay. And now the x minus 4 cancels out, the x plus 3 cancels out, and we're left with x plus 2 over x minus 3, comma, x is not equal to anything that made a denominator equal to 0 anywhere in this problem, including the beginning. So that means x is not equal to positive 3, because that's in the denominator right now, but it's also not equal to negative 3. So x is not equal to positive or negative 3 because of this denominator right here, and also 4, because now we put x minus 4 in the denominator, so 4 can't be x cannot be equal to 4 either, right? So even when you flip the fraction, right, you're not moving x minus 3, you're moving x plus 3 to the numerator, but it still was in the denominator at some point, so it still contributes to the excluded values, the thing that this function cannot, the variable cannot be equal to. Let's try it again. Factor, multiply by the reciprocal of the second term. So we got x minus 1 squared, that is a perfect square trinomial. X factors out, and we're left with x squared plus 1, which does not factor anymore, times, now the denominator goes to the numerator, factor out the 3, x squared plus 1, oh look at that, that's going to cancel, that's nice, and that's going to be x plus 2, x minus 1. All right, so one of these cancels with that one. This cancels with this. And we're left with an interesting expression here. Let's move the 3 to the front. Oops, equals. Let's move the 3 to the front. X minus 1, just good habit to get into, to put the coefficient in the front like that. And then we're going to leave the x in the front over x plus 2, comma. X is not equal to, you got a variable by itself, x is not equal to 0. Okay. Now we have this one that got canceled out, all right, because it's in the denominator now. So that's going to be a -2 for that one and a +1 for that. Now, this expression, x squared plus 1, if I set that equal to 0, when I take the square root of both sides, I get an imaginary number. So x squared minus 1 is never actually equal to 0. You can try it around if you want. If you can think of numbers, right? You plug in a positive number, x squared, you get positive. Plug in a negative number, you get a negative. Right? And if you think of it as a graph, right, it's a parabola shifted up 1. So it's never going to cross the x-axis. It has no roots. It has no zeros. Right? And so that expression, x squared plus 1, does not contribute to the excluded values because it's never actually equal to 0. Unfortunately, adding and subtracting is a bit more difficult. Okay, so if you remember how to add or subtract fractions, you might remember that you're going to need a common denominator. So if they have the same denominator, we add or subtract expressions by adding the numerators and placing the result over a common denominator and then simplifying if you can. Now, a lot of these problems here, we didn't, I didn't multiply these together. I didn't need to do anything because this is a pretty simplified form of this expression. I'm sure it's simplified because I can see all the factors and I know nothing else is going to cancel. That's not necessarily the case when we add or subtract, right? We might need to distribute things, add or subtract things, and then see if we can factor it and cancel. Right? So in this case, we have a common denominator. So when you have a common denominator, and right, it's just gonna be x, right? We're gonna put x squared minus 9 on the bottom, and that factors into x plus 3, x minus 3. Okay, so I know that no matter what happens with my numerator, that's what's going to be in my denominator. Okay, so because these are common denominators, we can just say that this is 5x plus 1 minus the whole second term, which makes it negative minus 4x plus 2. So that turns into x plus 3, which can then cancel. So we have 1 over x minus 3. And again, x is not equal to anything that made the denominator equal to 0 at any point in this entire problem. Let's try another. Let's try the checkpoint. I see a common denominator, so I know that's a good thing. Okay, so we're going to have x minus both of these, which then gives me negative 2x minus 2 over x plus 1. I can factor out a negative 2 and be left with x plus 1, which then cancels. So this expression is equal to negative 2, comma, x cannot be equal to negative 1. So basically it's a horizontal line with a hole in it. Right? But we'll talk about the graphs in a later section. It's not always going to happen that my denominators are exactly the same. So when we add or subtract rational expressions with different denominators, we have to find a common denominator. The easiest way to find a common denominator is multiply the two denominators together. And because we're considering rational expressions that have no common factors, the product actually gives you the least common denominator. And of course, we have to, manipulate the fraction we're multiplying both this fraction by d and both this fraction by b in order to get a common denominator of b times d. Now, we might have to do some manipulation and some thinking to get the least common denominator. We'll talk about that in a second. Okay? So these two expressions, the two denominators, have no common factors. Right? They have no common factors in their denominator. So what I'm going to do is I'm just going to take them, I'm just going to take them and multiply them together. So my new common denominator becomes 2x minus 3 times x plus 3. And that means that I need to multiply the x plus 2 times x plus 3 and the negative 4, the negative travels up, by 2x minus 3. Okay? And what I said before, that we have been leaving these expressions just kind of like this, worked for multiplication and division. It doesn't really work for addition and subtraction here. We really want to multiply this numerator. The denominator is fine, but we want to multiply the numerator together and try to simplify it as much as possible, and then see if we can factor it and cancel it with something else in the denominator. Maybe we will, maybe we won't. But first, let's multiply these two expressions together. Foiling them gives me x squared plus 5x plus 6. And then distributing the negative 4 gives me minus 8x plus 12 over 2x minus 3 times x plus 3. And now I can combine the like terms. And let's move over here to x squared. The 5x minus the 8x is minus 3x. And that's 18 for a constant over 2x minus 3, x plus 3. So now I got to ask myself, are there factors of 18? Does the numerator factor? Are there factors of 18 that add up to 3? And they're not, so the numerator is prime and it doesn't factor anymore. But what I still need to do is state the restrictions on the denominator. So that's going to be a 3 over 2 and a negative 3. Let's try another one. Denominator becomes x plus 1 times x minus 1, because x plus 1 and x minus 1 don't have any common factors. And we multiply the x minus 1 by the 3, plus 5 times x plus 1. A little bit easier here because we don't get a quadratic. So that's 3x minus 3 plus 5x plus 5 over x plus 1, x minus 1. And then we have 8x plus 2 over x plus 1, x minus 1. Now, I could factor out a 2. In fact, I'm going to. No, it doesn't matter. I thought something might cancel, but it doesn't. We're left with 4x plus 1. That doesn't really cancel anything. So I can leave this expression like this, and that's kind of good enough. Comma, x is not equal to anything that made the denominator equal to 0. So that's my simplified expression. What happens when the denominator does have a common factor? Okay, so that's when we have to find the least common denominator of several rational expressions. And basically, it's a polynomial consisting of the product of all the prime factors in the denominator, each raised to the greatest power of its occurrence in any denominator. So when adding or subtracting rational expressions that have different denominators with one or more common factors, you want to find the least common denominator. Okay, so again, if that was confusing, here's a step-by-step breakdown. First, factor each denominator completely. That makes sense. You want to see all the different factors. Then put everything in the first denominator and add to it anything in the second denominator that doesn't appear in the list. And we need the greatest degree, right, the greatest power of all of these different factors. And then multiply them all together, and you got the least common denominator. So what does that mean? It means if I have these two expressions and I want to find the least common denominator, I'm going to factor them. So here's a 5. Ooh, we can also take out an x. So 5x. So that's x plus 3. And this one factors into x plus 3 squared. All right, so here's what I do. I take everything right there. So my LCD, my least common denominator, is 5x times x plus 3. Then I say, okay, here are my 3 pieces to this, 5, an x, and an x plus 3. And you ask yourself, do any of these occur in the second one to a bigger power? Yes. Is there anything else in this expression? No. There's my least common denominator. So 5x, x plus 3 squared. Okay? You just take the biggest degree of every factor, right? So 5 occurs to the first power here. It occurs to a 0 power there. First power for x, 0 over there. 1 for x plus 3, 2 for x plus 3. So you're just taking the largest degree of every factor that is common to both. And even though you don't see them, these are common to both, which is why we can just write the entire first expression and then add to it anything that's missing. Let's try that again. Very similar problem here. So my first expression is factored x minus 3 squared, and the second one is x plus 3, x minus 3. Okay, take this whole thing. So this is my LCD. My least common denominator would be x minus 3 squared. And also, right, because it's first power there, second power there, so squared is the biggest one. And also anything that's not listed in the first expression. Okay? We don't need another one. You don't need to make this cubed. You could, but then it's not the least common denominator anymore. Right? And that'll make the problem a little more difficult. Okay? So when you find the least common denominator for 2 or more rational expressions, right, this is the first step that you need to do to add or subtract the expressions. So we're going to find the LCD. Sometimes it's as easy as multiplying the two denominators together. Sometimes we have to use some of the techniques that we just talked about. Okay. Then we rewrite each rational expression as an equivalent expression whose denominator is the LCD. Sometimes you can skip over this step if you sort of get the hang of this, and you just multiply the numerator and the denominator, then add or subtract, placing the resulting expression over the LCD, and simplify when you are done. And of course, state the variables that are excluded. So factor first. So we have x plus 3 over x plus 2, x minus 1, plus a 2 over x plus 1, x minus 1. Okay, so what's the LCD? The least common denominator is going to be x plus 2, x minus 1, everything from the first expression, and then the biggest degree or anything that's missing from the second one. Well, I already have an x plus 1 to the first power, so I don't need another one, but I do need an x plus 1. Okay? So then here's what I was saying is that you can eliminate this step, is you could go that we need x plus 3 times, well, what's missing, right? If we have an x plus 2, x minus 1, right? The only thing missing from the denominator would be x plus 1, so I need to multiply the numerator by x plus 1 as well. Plus 2 times something, well, I have an x plus 1, whoops, an x minus 1, I need an x plus 2. Okay, so the step you could have eliminated would have been this step right here. You could have just combined these at once. X plus 1, x plus 2, x minus 1, wrote it in a weird order there, but that's okay. Now, we're going to multiply these two together. We're going to FOIL them together to give me x squared plus 4x plus 3. We're going to distribute the 2. We put a plus because of the positive sign right there. 2x plus 4. We're now going to try, we're now going to try to combine like terms and simplify. So we got x squared plus 6x plus 7 over x plus 1, x minus 1, x plus 2. And then we are going to try to factor this. The factors of 7 that add up to 6. There are no factors of 7 that add up to 6. So that is my answer. My answer is x squared plus 6x plus 7 over the 3 of these. I'm not going to multiply them together because I don't want to. And you'll see later that it tells us more information in factored form. X is not equal to anything in the denominator that makes it 0. So plus or minus 1 and negative 2. Let's try that again. Let's try our checkpoint problem. Okay, so again, factor first. I'm going to go a little faster this time. I'm going to skip over one step. So this is going to be x minus 5 squared minus x minus 4 over, factor out the 2, x minus 5. Okay, so my common denominator is going to be x minus 5 squared. I got 2 there, I got 2, and a 2. Oh, I made this line weird. Let's put this in the middle. Okay, so what's missing? Well, from the left side, I'm missing this factor. I'm missing a 2 times that x minus everything here. So x minus 4 times what's missing from this denominator is another x minus 5. Okay, so don't get lost with the sign here because we're going to do the multiplication first. X squared minus 9x plus 20. 5 squared. And then let's distribute the negative and combine like terms. So we got, let's get a little bit more room here. So we got a 2x minus x squared plus 9x minus 20. The 2x and the 9x can go together. So we get a negative x squared plus 11x minus 20 over 2 times x minus 5 squared. We could try to pull the negative out and factors, and then when we do that, it'd be the factors of 20 that add to 11, but that doesn't actually work. So, comma, x is not equal to 5. That is the only variable in the denominator, right? We have an x minus 5 in both of them. The 2 is a constant. That is the only thing in the denominator. That's the only value of x that you could plug in that would make this expression 0 in the denominator. Okay, so complex rational expressions, also known as complex fractions, have fractions over fractions, have numerators or denominators containing one or more rational expressions. So look at the two examples, which we're going to simplify both of those in a minute. Both of those are complex fractions, fractions over fractions. One method to simplifying a complex rational expression is to combine its numerator into a single expression, and then to combine the denominator into a single expression, and then, because it's division, multiply the numerator times the reciprocal of the denominator. Now, personally, I think this method is a little harder than the one we'll look at next, but let's take a look at it anyway. Working with just the numerator. So the common denominator there is x, right? Because this is a 1 over 1. So we would have, now multiply this one by x plus 1. So there's my numerator. Denominator, same thing. We have a common denominator of x, and it becomes x minus 1. So then this is division. So we can take the numerator times the reciprocal of the denominator. The x's cancel, and we're left with, let's go down here, x plus 1 over x minus 1, comma, x is not equal to anything that was in any denominator anywhere in this problem, and so we get a 0 for the x and a positive 1 for this denominator. Okay? So that is the first method. Let's check that one more time. Combine the two fractions on the top, combine the two fractions on the bottom, then multiply the numerator by the reciprocal of the denominator. And 1 over x plus 3 over 4, so I have a little bit more room. The denominator here is 2x, so that becomes 2 minus 3x in the numerator, divided by the denominator here is 4x, and that becomes 4 plus 3x. So this becomes 2 minus 3x over 2x times the reciprocal 4x over 4 plus 3x. Okay, x's cancel, and the 2 hits the 4, and so distribute that, and we get 4 minus 6x over 4 plus 3x. Those do not cancel. Those are two binomials. You can only cancel across multiplication or division, not addition and subtraction. X is not equal to 0 and negative 4 over 3. Okay. Now, personally, I think that method is a little bit more difficult than the other method, than this method. So a second method for simplifying a rational expression, complex rational expression, is to find the least common denominator of everything, of all the rational expressions in the numerator and the denominator. Then multiply everything by this least common denominator, and it has the effect of clearing all the fractions. So we saw that the least common denominator in the first problem was x. So if we multiply the top and the bottom by x over x, look what happens. We just get x plus 1 over x minus 1. And now we're done. Okay? So a little simpler than trying to combine the two fractions and then multiplying by a reciprocal. Okay? If you multiply every term in the expression by the least common denominator, it clears the fractions and gets you right to the end. So let's do that with this expression. Okay? The denominator there is 1. So the least common denominator of this expression is x plus h times x. Let's rewrite it the other way. So x times x plus h. If I do that to the top, I have to do that to the bottom as well. Okay. So then when I multiply the fraction times x times x plus h, the x plus h's cancel, and I'm left with just x, minus, in the second term, the x's cancel, and I'm left with x plus h, over, nothing cancels here because we don't have any fractions, so it's x times h times x plus h. Here we can cancel those two, and now we have a negative h over xh, x plus h. H's cancel, and we're left with a negative 1 over x times x plus h. This expression comes from something called a difference quotient, which is very handy in calculus because it's the basis of finding limits. And basically, we couldn't plug a 0 into this expression before because h is not equal to 0, and x is also not equal to negative h, or x is not equal to 0 as well. But all that, if we wanted to plug in a 0 before, we couldn't, but now we can. Interesting. Or sorry, if we wanted to plug in a 0 for h, be more specific. We still can't plug in a 0 for x, but we could plug in a 0 for h. Let's try that again. The common denominator of this entire expression of all three terms, of the first term, the second term, and the third term, is x plus 7 times x. So we're going to multiply the bottom and the top by x times x plus 7. And that cancels the x plus 7 there, and we're just left with x minus the x's cancel there, x plus 7 over, a little simpler when this is numbers, right? Because then these two cancel. We have a negative 7 over 7x times x plus 7 cancel, and we're left with a negative 1 over x times x plus 7, where x is not equal to 0 or negative 7. Much simpler this way. Even going back to this expression, right, if I would just take the common denominator of everything, which would be 4x, if I multiply the numerator and the denominator by 4x, I would get 2, right, I would get a 4 because the x's cancel. And here I would get a 2, so it would be negative 3 times 2x over the x's cancel there, 4, and then the 4's cancel there. And look at that. Much faster, much simpler, I think, anyway. All right, so how about some fractional expressions in calculus? So fractional expressions containing radicals occur frequently when we're dealing with calculus expressions. And because of the radicals, these expressions are not rational expressions. However, you can still use the same technique. So technically, an expression like this is not a rational expression because it has fractional exponents. But we can use the same technique of multiplying everything by the common denominator, right? This is over 1, this is over 1. The common denominator is just the square root of 9 minus x squared. So if I multiply the top and the bottom by that, a square root times a square root, same base, right? Add the exponents together, we just get 9 minus x squared plus x squared over, because the radicals cancel, over 9 minus x squared times the square root of 9 minus x squared, which is really 9 minus x squared to the 1/2 power. So that means that we can do some nice addition here. These two cancel, and so my expression becomes 9 over 9 minus x squared to the 3 over 2 power. That is simplified. If you wanted to get fancy, you could even rationalize this denominator and multiply by 9 minus x squared to the 1/2 power. And so my rationalized expression would be 9 times 9 minus x squared to the 1/2 over 9 minus x squared squared. So again, just a nice technique that can help us to simplifying a fractional expression with radicals. Let's finish at this point instead of going to rationalize it with our checkpoint here. Okay, so we have the square root of x plus 1 over the square root of x over x. Denominators, right? There's 3 terms here. Denominator here is 1, denominator here is 1. So I'm going to multiply everything by the least common denominator of every term, which is just the square root of x times 1 times 1. Square root of x times square root of x is x plus 1 over, right? The square roots cancel, over x times the square root of x. So that's would be to the x plus 1 over square root is 1/2. So that's 3 over 2 power. 1 there, 1/2 there. Let's finish by looking at, again, an expression here with these x's and with these h's. These things, again, come from something called a difference quotient. And so you can see that this expression is not defined if h is equal to 0. However, later in calculus, you might ask the following questions. What happens to the expression as h takes on values that get closer and closer and closer to 0? Okay. So when you're in this form, when you're in a form with something that can't be equal to 0 in the denominator, it might be helpful to put it into a different form. And now we can use a technique called rationalizing the numerator. Usually you don't want to do that, but again, in calculus, you might want to. So this process involves rewriting fractional expressions as an equivalent expression in which the numerator no longer contains radicals. And guess what? We just multiply by the conjugate. So let's finish this by looking at this expression, x plus h minus the square root of x all over h. I don't like it the way it is. I want to rationalize the numerator, so I'm going to multiply by the conjugate. This first term stays the same. The second term is the opposite. And we now have a squared minus b squared when we multiply two conjugates together, which is just x plus h minus x. Well, that's nice because now we have h times this other numerator, x plus h, plus the square root of x. These two cancel out because they're opposite. Now these h's can cancel out because it's the only thing left. And so now I have 1 over x plus h plus the square root of x. And we were able, and of course we can say that x can equal 0, negative h, and h can't equal 0 either, if we want to put all the restrictions on the variable. But what we can see now is that I couldn't have put this, I can't put 0 into this expression to the original, but now I can put it into this expression. So even though the original function was not defined at h is equal to 0, this is a thing with calculus, we can figure out what the expression is as h gets very, very close to 0 and what it would have been if h could be 0. And in this case, it would be 1 over 2 radical x, 2 square root x. Let's do one more and we'll wrap this up. So we get x plus 3 minus the square root of x. A little easier here because there's no h's. And we're going to just multiply by the conjugate of the numerator, giving me x plus 3 minus x over 3 times all this stuff. And cancel those two, they're opposites. Now we have 3 over 3, which can reduce. And so my answer becomes 1 over the square root of x plus 3 plus the square root of x, where x cannot be equal to anything that makes the denominator equal to 0, which actually, because this is a binomial, is nothing. And I take that back for this one up here, right? So x could be equal to 0 or negative h, right? Because this is a binomial expression. Okay. All right. Well, with that, we are finished with section P6, Rational Expressions.